All right, welcome to this high-yield explainer. Today, we are fully decoding complex biostatistics and honestly, turning them into a super practical, incredibly high-yield clinical toolkit. If you've ever felt like clinical data and statistical math were just this massive, tangled web, well, get ready. We're going to untangle the whole shebang and make these concepts finally stick.
But before we really get rolling, I want to say thanks so much to Assistant Professor Dr. Farhad Mustafa Musa Atrushi, MD, Board of Certification in Orthopedic Surgery. We actually have the privilege of presenting this explainer as a structured clinical lecture built directly from Dr. Atrushi's source material. So whether you're an orthopedic resident, a med student, or just a clinician looking to absolutely conquer your board certification, consider this your ultimate roadmap to mastering basic science and statistics for orthopedic surgery. Here is our roadmap for today. We'll cover the foundation of clinical data, evaluating tests in patients, population risk and impact, statistical traps and decisions, and wrap up with essential orthopedic clinical metrics. Let's dive right in. Module 1, the foundation of clinical data. Let's start with the absolute basics.
In a perfect world, your data falls into a beautifully symmetrical normal distribution. You know, a classic bell curve where the mean or the average sits right dead center. But let's be real, clinical reality is rarely perfect, right? When we hit extreme outliers, say a patient with an unusually long recovery time, we get a skewed distribution. Suddenly, that average gets pulled way off track, and that is exactly why, for skewed data, looking at the median is absolutely vital. It gives us the true middle ground without getting dragged around by those extreme outliers.
Moving on to Module 2, evaluating tests and patients. Let's shift from raw data to our daily diagnostic tools.
Okay, the 2x2 table. This is our ultimate clinical baseline. It simply maps the actual presence of the disease against our test results, which creates 4 very distinct realities for us: true positives, false negatives, and true negatives. Nailing down this grid is step 1.
And from that exact blueprint, we unlock 2 absolutely crucial memory tricks: SNAN out and SPEW in. Think about it. A highly sensitive test captures almost everyone who actually has the disease. So a negative result confidently rules it out, SNAN out. It's totally perfect for screening. On the flip side, a highly specific test rarely triggers a false alarm. So a positive result confidently rules the disease in, SPE in. Perfect for confirmation. But hey, what about evaluating the actual patient sitting right in front of you? Well, that requires positive and negative predictive values. If your patient gets a positive result, what are the actual real-world chances they have the disease? Here is the crucial distinction you have to remember. Unlike sensitivity and specificity, predictive values are heavily dependent on the baseline prevalence of the disease in the population. If a disease is just incredibly rare, even a fantastic test is going to yield a lot of false positives. Module 3, population risk and impact. Let's translate these stats into broad clinical impact. When we're measuring a population, we use 2 terms that honestly get confused all the time. Think of incidence like a running faucet. It's measuring newly reported cases over a specific period of time. Prevalence, on the other hand, is the water already sitting in the tub. It's the total number of cases at a single static point in time. Now, let's look at a classic board exam trap: relative risk versus odds ratio. Before we even touch the math, you really have to understand their distinct study origins. Relative risk comes from prospective cohort studies, so looking forward in time, while odds ratios come from retrospective case control studies, looking backward in time. And the math here actually hides a massive clinical trap. The odds ratio only mathematically approximates the relative risk when the disease is rare. And by rare, we specifically mean occurring in less than 10% of the population. So how do we actually explain this to a patient? Let's take colon cancer screening as an example. Say the absolute risk reduction between the control group and the treatment group was 0.1%. The equation for the number needed to treat, or NNT, is simply 1 divided by the absolute risk reduction. So 1 divided by 0.001 equals 1,000. What does that mean? It means you literally must treat exactly 1,000 patients to achieve exactly 1 additional favorable outcome. All right, on to Module 4, statistical traps and decisions. Whenever we analyze data, we can make errors. A type 1 alpha error is essentially a false alarm. You reject the null hypothesis, claiming there's an effect when reality says there isn't one. A type 2 beta error is the misdiagnosis. You accept the null hypothesis, claiming there's no effect when there actually is.
Crucially, type 2 errors are directly linked to study power. If a study is underpowered, you simply just do not have enough data to see the true difference.
So, knowing these traps exist, I've got a question for you. How do you choose the exact right statistical test for your specific data? It's a question that haunts a lot of test takers for sure, but it really doesn't have to. The analyst's decision tree removes the guesswork entirely. It all starts with one simple question. What type of data do you actually have? If your data is categorical, like eye color or blood type, you head straight to tests like chi-square or Fisher exact. If it's continuous, like blood pressure or a patient's height, you look at how you're comparing your groups. Comparing 2 groups leads you right to a t-test, while comparing 3 or more groups leads you to an OVA. Honestly, just following this logic tree takes the fear right out of statistical models. But, even with the perfect tests, literature can still be biased. To detect publication bias, we use what's called a funnel plot. A healthy, completely unbiased collection looks like a perfect symmetrical triangle. You've got large studies tightly grouped at the top and smaller studies scattered evenly across the base. But you really have to beware the missing wedge. If the plot is heavily skewed, it clearly signals that negative studies are just being swept under the rug and not published. Finally, Module 5, Essential Orthopedic Clinical Metrics. Let's bring this all back to the patient. When we're tracking long-term joint replacements, survivorship analysis using the Kaplan-Meier method is absolutely essential. But perhaps the most vital concept to remember overall is the MCID, the minimal clinically important difference. This is what reconciles pure math with clinical reality. Because look, a difference might be statistically significant on paper, sure, but if the patient cannot actually feel the improvement, it kind of doesn't matter. MCID is the difference that truly matters to the patient.
Before we wrap up, I want to say thanks so much again to Assistant Professor Dr. Farhad Mustafa Musa Atrashi, MD, Board of Certification in Orthopedic Surgery, for providing the amazing framework for this lecture. Now I want to leave you with this. How will you actively apply this decoded statistical toolkit to elevate your very next patient encounter or journal club reading? It's time to transform your practice. Thanks for learning with this explainer.